Again, and welcome back to AUD 518, also known as hearing conservation. Today, we will have an overview of some of the parameters of sound, and we'll also talk about anatomy and physiology of the hearing mechanism. Before we get into that, I want to orient you to a link here that is available to you in the course syllabus. If you select this link, it will take you to a spreadsheet where it will have a list of links to videos that I've shared with you throughout the semester. So right now, the only link that you need to be concerned with is this first one, which is the link to the Introduction to Hearing Conservation syllabus overview. Okay, so you'll be able to navigate to this spreadsheet throughout the course of the semester because I've shared it with you. You are second year AUD students, and that includes all of you here. If there is someone missing from this list, please let me know and I will add you. All right, so onward to the lecture for today. Okay, now on to our little overview on the introduction to sound. If you haven't already had a chance to look, this is the cover of the text that we'll be using for this course, titled Hearing Conservation in Occupational, Recreational, Educational, and Home Settings. The author of our text is Vishaka Waman Raul. The chapters that we will discuss are outlined in the course syllabus. You will be responsible for reading those chapters as well as completing the assigned activities and projects associated with each module. So we're going to have a very quick overview today of the major concepts associated with sound. We'll talk about the nature of sound as well as parameters of sine waves. So there are three physical quantities of sound that we need to talk about, and those include elasticity or stiffness, restoring force, and friction. So some materials resist changing in their shape, like a spring, for example. If you compress it and let it go, it springs back to its original shape. The property that makes a deformed object return to its original shape is called elasticity or stiffness. The more readily it returns to its original shape, the more elastic or stiff the object is said to be. The force that opposes the deformation of an elastic material is called the restoring force. The restoring force depends on two factors, including the elasticity or stiffness of the material and the amount of deformation. When one object rubs against another object, the force that opposes the motion is called friction. And friction depends on two factors, roughness and the velocity of the rubbing motion. It's also important to note here that friction produces heat. So simple harmonic motion, what is this? So when we talk about simple harmonic motion, we're just talking about a vibration that is defined as the back and forth motion of an object. And this is also called or termed an oscillation. Examples of vibrating objects include a guitar string, a pendulum, the prong of a tuning fork, and vibrating air molecules or particles, which are responsible for sound. The simplest form of sound vibration is produced by simple harmonic motion. Simple harmonic motion occurs when a force is applied to an object like a tuning fork that has both elasticity due to stiffness and inertia due to mass. So let's take a quick look and see what happens when a force is applied to a tuning fork. So here's a figure that will walk us through what happens when a force is applied to a tuning fork. The force is applied, and then the prongs move inward. But because of the elasticity or restoring force, they are slowed down and they reverse in the opposite direction. So the tuning fork wants to resume its original shape. And as the prongs move outward again, they overshoot their original position due to inertia. But again, we have elasticity or the restoring force, which causes them to slow down, stop momentarily, and reverse direction again. So they pass through their original position due to inertia, and the entire process repeats itself over and over and over again. So the vibration of the tuning fork transmits to the surrounding air molecules, and they too are oscillating in simple harmonic motion. Sounds produced by objects vibrating in simple harmonic motion are called pure tones. So here is a figure that's showing the compressions and the refractions of the air particles that are resulting from the vibration of the tuning fork. So in these lighter areas, you've got what are termed rarefactions, which is where you've got space where the particles are spaced out. And then you've got compressions, which sounds exactly what it's like. Which is exactly what it sounds like. You've got bands or areas where the particles are bunched up together. Okay, and those are called compressions. And as the sound propagates through the air, you have these different bands of compression, rarefactions and compressions. So a characteristic of simple harmonic motion is that the timing or rate of oscillations stays constant. So each complete repetition of the motion is called a cycle, and the number of cycles that occur during each sound is the frequency. Units of frequency are cycles per second or hertz. Even though the rate of oscillations remains constant, the excursions of the tuning fork gradually decrease over time due to friction with air molecules. So the dying out of oscillations over time is called damping. So here we have a graphical representation of displacement over time, and we call this a waveform. So we're just graphing what happens to this tuning fork over time. All right, so on our x-axis, we have time, and on our y-axis, there's displacement from the center resting position. So in our figure here, we can see that the applied force is happening initially, and then we've got these periods where the restoring force and inertia take over, causing the tuning fork to overshoot and want to return back to its original position and going out too far, and then coming back inward and then going outward again. And then we can see over time that the amplitude of the waveform is reduced, and that is what we term damping due to friction. Okay. So the inward movements of the tuning fork are plotted upward, and then the outward movements of the tuning fork are plotted downward. All right, so how is sound propagated through the air? So we have oscillations of each air particle that are transmitted to the next particle adjacent to it. So each particle oscillates around its own resting position. So here we've got our tuning fork, and we've got 5 different types of particles. Okay, so each particle oscillates around its own resting position. However, the sound wave moves through the air as each particle sets its neighbor into motion. So they're kind of knocking into each other, but they're not moving. No one particle is moving across the entire waveform. So the sound wave moves through the air as each particle sets its neighbor into motion. And the sound propagates outward in all directions from the sound source in a sphere. Okay. Sound waves and other waves that repeat themselves over time are called periodic. Sine waves are the simplest kind of periodic waves. So some parameters of our sine waves include the cycle, which is one replication of a periodic wave, our period, the time it takes to complete one cycle, frequency, number of cycles that occur per second, and then wavelength, the distance traveled by the wave in one period. Once we have identified one cycle of a sine wave and determined the period, we can calculate the frequency, which is one cycle over the period, F equals 1 over T, and the unit is in cycles per second, or hertz. We can also calculate the wavelength, which is equal to period in seconds times C, which is the speed of sound in air. And here we're going to refer to the speed of sound in air as 344 meters per second. So here's an example. We've got our sine wave. On our x-axis, we have time in milliseconds. The amount of time it takes for one cycle of completion of this sine wave is 4 milliseconds. So our period for this example is period, or T, is equal to 4 milliseconds. So if a period is equal to 4 milliseconds, then what is the frequency? So recall that frequency is equal to one cycle over the period in seconds. So we've got one cycle over 4 milliseconds. We need to convert milliseconds to seconds because frequency is 1 over period, which is in seconds. So we divide by 1,000 and we get 0.004 seconds. So 1 divided by 0.004 gives us a frequency of 250 cycles per second, or hertz. We can also calculate the wavelength. If the period is equal to 4 milliseconds, then we can calculate wavelength by taking the period in seconds and multiplying it by the speed of sound in air. So 4 milliseconds times 344 meters per second. So again, we have to convert to seconds. So take 4 and divide it by 1,000 and you'll get 0.004. So 0.004 seconds times 344 meters per second gives us a wavelength of 1.37 meters. Seconds cancels out, by the way, so you're left with meters. That's why it's only meters and not meters per second. Okay, additional parameters of sine waves include the amplitude. So amplitude refers to the size or magnitude of a sine wave. It may be specified in units of power, intensity, or pressure. So there are different metrics for amplitude. So you might see amplitude referred to in peak amplitude, which is its instantaneous positive going peak. Peak to peak amplitude, which can be the amplitude from the tippy top peak to the trough. You can also report amplitude in root mean square, or RMS, where you would take the peak amplitude and you would multiply it by 0.707. So again, to summarize, parameters of sine waves include the cycle, the period, frequency, wavelength, peak amplitude, peak to peak amplitude, and RMS amplitude. So to summarize today's brief review of sound, there are 3 physical quantities of sound that we're interested in, and those include elasticity, restoring force, and friction. Sound propagates outward in all directions from the source, and the major parameters of sine waves are cycle, period, frequency, wavelength, and amplitude. So take a break. This is the end of the introduction to sound review. So take a break, rest your eyes and your ears, and I'll see you in a bit for the review on anatomy and physiology of the ear